2211, lab report for lab 2, projectile motion. So what is this lab? Basically, this is a lab where we threw a paper ball with a X and Y component, meaning it's not just straight up and it's not just straight horizontal. It was kind of thrown at an angle in relation to the ground. We defined the system as the paper ball, the surrounding as the air producing a drag force on the ball, and the earth producing a gravitational force on the ball. You can see in the bottom of the screen, this is the video that we recorded when we did the experiment. Then what we did is we simulated the same experiment. We actually simulated it twice, one accounting for drag force and one not accounting for drag force. You can see all the important code below. Also, at the very bottom right-hand side, you can see my glow scripts, like the URL for my glow script. You can look at that if you want. It's not going to tell you too much more than I'm going to tell you right now. These are all the initial conditions that we set, and this is the important part of the loop. So basically, we put in all the real-world data of the mass, position, velocity of the ball that was thrown, and then in the while loop, we use the position update and velocity update formula, which I'll get into more in the next slide, to update and create graphs and simulate the real world, right? This data, as you can see, B is the drag force constant. So here B is 0.002, 0002. So this is the one accounting for drag force. However, we did another simulation where B was equal to 0, and I'll show you the data that we got from both. Finally, what we're going to do is we're going to compile the real world simulated data and see how they compare and contrast. So what is the lab trying to prove? Well, it's trying to prove that something in projectile motion, so something like thrown in the air, like this paper ball, will only have forces of gravity and drag on it. Or actually, the only force that we need to account for are gravity and drag. So it proves this. It's also trying to prove the velocity update and position update formula, which you can see in bullet points 2 and 3. Those are the v final equals the other side of the equation, and the r final equals the other side of the equation. Those are the velocity and position update formulas, respectively. Basically, these are the two formulas that we used previously in the simulated data, and if these formulas are true, then our simulated data will look like our real-world data. Basically, the lab is trying to prove that these functions are real because we use these functions in the simulation. If the simulation aligns with the real world, then it basically proves that the real world uses these same functions. This lab is also trying to prove that drag is important to calculate, which is the reason why we simulated we have two different data sets simulated, one of which accounting for drag and one not. Theoretically, the one that accounts for drag should be closer than the one that doesn't, but we'll see on the next slide. In case you're wondering, on the right-hand side here, we have a graph of the simulated data on the top and an image from the real world when we're getting data from the real world. So here is the data that we collected. First off, to explain these graphs, you can look at the keys, but I'll explain it for you. Basically, the blue line is the real-world data. It's a little shaky because there's a very short amount of time that we're accounting for. So it starts at like 0.2 seconds, ends at 0.9 seconds. So only about 0.7 seconds there of data that we collected. So very short time span. Could account for some error, just human error. Also, it could be that I put in the wrong that the initial conditions for the simulated data might be a little bit off. Again, it's just human error of us trying to calculate the initial velocity, initial position, all that kind of stuff. Could just be human error for why there's small discrepancies in the simulated and real-world data. Then the yellow graph shows the simulated data with drag calculated for, and the red graph shows simulated data without drag accounted for. Some of the assumptions we made when coding this is obviously when we did the red graph, we accounted for no drag. When we did the yellow graph, we accounted for a constant drag coefficient, which means that we said, our paper ball, no matter what direction it's facing, it'll have a constant drag, which obviously isn't true because the paper ball isn't a perfect sphere like we theoretically hope it is. So drag force from one side is going to be different from drag force from the other side, but it's relatively the same. So we just said it's roughly constant. And again, some error that this could be accounting for is that there is is just human error. We mess up things. But as you can see, the drag force, the simulated data with drag force is much closer to the real data than without drag force, showing that we do need to account for drag force. Some of the frequently asked questions: do our simulations show terminal velocity? So, little heads up, on the right-hand side, we have the top graph shows without drag force, bottom graph shows with drag force. The top graph does not show terminal velocity because it's a straight line. We would expect that straight line as t goes to infinity would just keep getting, we'd have a more negative and more negative and more negative velocity, and it would never bottom out. However, the bottom graph shows a slight curve. Hopefully you can see it. I tried to enunciate it, but it might be a little hard to see. It does curve towards, so it increases less the further along we go. So we would expect that at a theoretical infinity, it would bottom out at some final velocity, which would be its terminal velocity. Finally, the final question we have is, what if the object were thrown straight up? This is with the same magnitude of velocity, meaning that the velocity in the y direction would be greater. Using the velocity update formula, we can figure out that means that the entire graph of velocity versus time would be greater, which makes sense. You start with more upward velocity, then the entire graph for upward velocity will be greater. However, that then correlates to using the position update formula. That means that, with the same starting and ending locations being at like the origin, y equals 0, then with a greater velocity in the y direction graph, it would increase the amount of time that it would take, which makes sense. You throw something harder up, then it'll take longer for it to get back to you. Thank you for listening.